Hello, thank you for coming. I'm Junho Choi. Today, I'm gonna talk about my paper, Position-Based Augmented Reality Platform for aiding construction and inspection of offshore plant. And here are the contents: introduction, proposed method, experimental result, conclusion. Let me start. Introduction. In construction and inspection fields of offshore plant, there are many attempts to reduce the time and cost. The traditional method uses 2D drawing and 3D CAD model, but it is not intuitive and can be confusing when the product is complex. In order to solve these problems, nowadays augmented reality AR is applied which can provide the direction or design efficiently. AR operates stably in a completed offshore plant environment as shown in videos. However, existing AR solutions do not work well in the fabrication of offshore plant because of various challenge constraints in the working site. There are various challenge constraints in the construction site of offshore plant. First, markers cannot be used in most areas. They may not be visible due to obstacles or covers and can be damaged during the fabrication process. Second, strong magnetic disturbance caused by steel structures can make it difficult to apply magnetometer. Third, GPS signal cannot be used because structure parts may block the signal from the sky. Fourth, additional devices such as Wi-Fi router or beacons cannot be used in such environments because they are prohibited for security reasons. Fifth, there may exist several temporary objects such as scaffolds, machines, wires, and supports which are not defined in the CAD models. In addition, some parts such as pipes or machine are often wrapped or covered for protection so that the actual geometric shape are not visible as shown in figures. Lastly, workers are not allowed to wear any devices that may compromise their safety. In this paper, we propose an AR platform for the fabrication and inspection of offshore plant while overcoming the constraints mentioned above. The core idea is to track the user's position independently without any visual input and combine it with the AR method. This way, we can solve the problem that the existing AR method have when they are used for a large-scale industrial applications such as error accumulation caused by loss of visual pictures. We use an accelerometer and gyro in an IMU module to deal with the second, third, and fourth problems. Workers wears the IMU sensor on the ankle and holds a mobile device in their hand or put it in the pocket. They do not compromise the worker's safety while moving or walking. This proposed tracking module tracks the position of worker by using the accelerometer and the gyro. It does not require any extra sensors or marker except at the entrance of the region of interest. We employ tracking and registration to solve the first and fifth problems. This registration module computes the accurate camera pose for proper augmentation and overcomes the limitation imposed by the fifth constraint. Next, research goal. In summary, we propose the novel AR platform for the fabrication and inspection of offshore plant in this paper. The proposed AR platform is designed to work in the use case written in the paper. Please check the use case in the paper. Anyway, the main contributions of this work are as follows. First, we develop an AR platform that can be used in challenging environments such as construction site of offshore plant. Second, we propose enhanced IMU-based user tracking method in the area, with the challenging constraints. Lastly, we propose primitive fitting-based filtering and registration method for registering the scan data with the corresponding CAD model to robustly manage any noise and outlier. Overview. The overall structure of the proposed platform and data flow is as shown in the figure. The starting position and initial moving direction of the users are initialized using two markers that are separated by 1 or 2 meters. Once the initial setup is completed, tracking is started using the PCA-based user tracking method. Here only an IMU is used. In a target location, they determine the position and viewing direction of the mobile device using registration between the actual target object and the corresponding CAD models. The estimated position and direction of the device are used to correctly display the CAD model and necessary information onto the target object onto the screen of the device. This slide represents the detail of the overall structure with the data flow. Next, propose method. First, hardware design. The hardware design consists of mobile, IMU module, and RGBD sensor. The mobile performs tracking, scanning, registration, data communication, and visualization. And the IMU sensor transmits sensor data to the mobile through Wi-Fi. Finally, the LGBT module acquires the depth information in real time and sends it to the mobile. The AR mobile device has these computation modules: tracking, registration, visual SLAM, and AR. First, the tracking module. The tracking module tracks the user's position and direction using the IMU data. The overall process of tracking is shown in figure. In user distance estimation, the measurement data from the IMU are given to the AHRS module to determine the transformation between the sensor and the motion coordinate systems to obtain the linear acceleration components in the motion plane. The AHRS approach works with the 60OF or 90OF data. In our case, we employed the 60OF method because fairly strong magnetic disturbances are experienced in the application domain. Anyway, we can perform the stat detection using mean variation of linear acceleration. And then we can compute the user distance estimation for each step using double integration of linear acceleration with JUPT algorithm. Next, user direction estimation. Firstly, remove the linear acceleration noise using low-pass filter. Then we compute the eigenvalues and eigenvectors of covariance matrix of the x and y components of linear acceleration are computed, among which the eigenvector corresponding to the register eigenvalue is taken as a possible user direction using PCA. This process is not necessary in the 90OF method, but this method was used to do without gyro data in the 60OF method. Anyway, through these processes, we can perform real-time user tracking using user distance and direction estimation. The parameters used in the algorithm are written in the paper, so please refer to them. Next, the tracking results. We performed the various tests in the environments where some of the constraints mentioned in the paper were imposed. We evaluated the performance of 60OF, 90OF, and the proposed method on machine learning. The results show that 90OF yields significant error accumulation as shown in the figure. On the other hand, the 60OF and the proposed method show more accurate result. However, 60OF method experience a problem with rotation as can be inferred from the test of machine learning. These tests show the better performance of the proposed method than others. Case of the offshore plant. In this experiment, similar results to the previous slide were presented. This test also showed that the proposed method is more accurate than the others. Next, Visual Slam module. The Visual Slam module is used for two purposes. First, it estimates the camera pose for AR. It can perform local localization. Then second, it generates the depth information using mapping function in SLAM. The scan data are then used in the registration module. In the study, we applied the ORB SLAM method with an RGB-D camera. It can compute the camera trajectory in real time and perform a 3D reconstruction of the scene by extracting and matching the ORB pictures. Next, registration. The registration module estimates the pose of the device through registration between scanned point and CAD model. The overall process of registration is shown in figure. First, filtering with ROI selection. The acquired point cloud includes noise and the parts that are not defined in the CAD model, such as scaffold temporary supports. Therefore, we detect and remove the parts that are not defined in the CAD model from the scan point set using the primitive-based filtering method. After that, we can acquire filtered point clouds, and we apply the Poisson disk sampling method to the CAD models to obtain point cloud, because CAD model has sparse point clouds. Then we take the point inside the box of RI at the current position. Finally, we can registration modify point cloud and CAD model. We use the superpopCS method to obtain an initial registration result, and the initial registration result in further refined by the ICP-based algorithm to compute the final transformation matrix. The transformation from the registration module is used to match the camera pose in the real and model spaces. It is given to the Visual Slam module and used as the starting pose. Next, the device's camera pose is tracked in real time while the device moves. Once they are aligned, the CAD models and information can be properly augmented on the device's screen. Our platform can be used for assisting in fabrication and inspection. Therefore, our platform includes not only augmentation of the CAD model, also simulation and inspection by comparing inserted parts and CAD model as shown in the figure. Next, experiment results. That section presents only the result from offshore plant. Figure shows the actual route and estimated path obtained using the proposed method. A worker followed the path line marked in the test area. We performed the test 3 times. Table summarized the experimental result. Here, the accuracy of tracking is evaluated by computing the distance between the designated target position and the tracking result. The average error is approximately 1.76 meter for the route length of 62 meter. This amount of error is allowed in our target application. The acceptable accuracy in our application is about 5 meter or less. Next, registration. We use the Visual Slam module to scan the surrounding area near the position at which the worker stood. We obtain approximately 50,000 3D points. Next, we perform the primitive fitting-based filtering and registration procedure to align the point clouds. Figure shows the point clouds and CAD model before registration and after registration. Registration results are summarized in table. The average computation time for registration, which includes filtering, initial registration, and registration, was 5 seconds. The average registration error was 16.3 millimeter. This is augmentation results. Through the results of the previous processes, it can be seen that the CAD model is well augmented on the part of the real world. This is a demo video that includes the overall process. I don't have enough time, so I will show it at double speed without explanation. This video is uploaded online with the paper in Visual Computer Journal. This video shows the results of testing the integrated application on an offshore plant. In the video, you can see that tracking is well done without visual input. When the worker arrives at the location, the visual slide module is performed and the worker acquires a point cloud. The obtained point cloud is registered with the corresponding CAD model using registration module. After that, you can see the AR visuals such as augmentation of CAD model or simulation. This is a rest page conclusion. In this study, we propose a novel AR platform that helps workers to perform fabrication and inspection of offshore plant under construction efficiently and correctly. The developed solution can be flexible extended to other use cases. For example, in a building or bridge construction site, a worker can figure out what needs to be done at a particular position by watching instruction and design information associated with the location. Despite these advantages, the proposed method has certain limitations. First, we need a new method to track the user's position only using a mobile device so that we are able to eliminate an extra IMU sensor. Second, we have to introduce a method to initialize the user's position and direction without markers before the position tracking begins. Third, the proposed method needs to be improved using the device with state-of-the-art technology such as LiDAR or depth sensor. Although they are not serious issue in our target application now, they need to be solved for the proposed platform to be used for general applications such as museum and large malls, which is recommended for future work. Thank you for listening.